Welcome, IB Chemistry, to your textbook and your first set of notes. Truth be told, the history of the atom, there's not going to be an IB or AP test question that asks you who discovered what. However, it is nice to have a foundation that our understanding of the atom is based on models, and those models change as we gather new information about what's going on inside of an atom. So every time we do an experiment, we learn something new, we change our model to incorporate the new stuff. With that in mind, your notes start out with Dalton, the father of the modern atomic theory, at least as far as European history goes. And on page 58 of your book, they do a nice job of describing an atom. The smallest unit of the element is a good way to describe that. It's the smallest particle of matter that can engage in chemical reactions. You can break down an atom into smaller pieces, but then it ceases to be that element if you do. If you go on to the second page, we have 5 postulates or observations that Dalton makes. You can list those in your notes as the 5 main postulates of the atomic theory. Again, you kind of want to know the basic ideas here, not really a memorized thing. But he believed that atoms were tiny, indivisible particles. In fact, the word atomos means indivisible, and that turns out not to be entirely true, that we can break down atoms into smaller pieces. We just didn't know that back in 1808. He also believed that atoms of the same element were alike in every way. That's that third one. We didn't understand isotopes yet, and that you could have different flavors of the same element based upon the number of neutrons and thus the mass. All right, the electron is described here on page 60. Let's see. J.J. Thomson discovered that all materials seem to have these tiny negative particles that they could pull out of stuff. And he had this plum pudding model, which is pictured here on the side. This pink circle, basically a positive background with negative specks in it. Those negative specks called electrons, and you could pull them off of an atom. Rutherford did his famous alpha particle scattering experiment involving gold foil. That is described down here on page 60. If you're not sure what an alpha particle is, it is described as a helium nuclei, or in other words, a nuclear particle of 2 protons and 2 neutrons, which of course would have a positive charge, hence the protons. Dalton expected that most of these particles would go straight through the gold foil because the positive background matrix really had no real substance to it, and the electrons were so tiny, he thought it'd be kind of like shooting bullets at tissue paper. And indeed, most of the particles did go straight through, allowing him to kind of conclude that an atom was mostly empty space, mostly nothing, that you can go right through it. However, every once in a while they'd hit something so dense and positively charged that things would bounce back from there. And so he had to develop a new model of the atom that had a dense positive charge, hence he called that the nucleus, borrowing a term from biology to describe the atom. Because the electrons are now on the outside and the positive stuff's in the middle, if the electrons were stationary, they would fly into the middle. Just like if the moon was stationary, it would fly into the Earth based upon a gravitational attraction. Here we also have an opposite attraction. And so the electrons have to have some kind of motion that keeps them in orbit, where you have a balance between the attraction and this attempt at escape velocity. And between the two, you develop some kind of orbital rotation. Over here on the bottom, page 61, we've got a basic chart describing where the particles are in an atom. Protons have a mass of about 1, neutrons about 1. Electrons are fairly close to 0. Not actually 0, but compared to a proton or a neutron, very, very, very tiny. And the charges are +1, -1, and 0. I did notice that the chart in your notes has neutrons and electrons switched, so keep your labels straight as you are entering things from the book into your notes. Atomic number is mentioned at the bottom of page 62. Atomic number, it's the defining property of an element, so a structure is carbon if it has an atomic number of 6. That's also the same thing as the number of protons. There that is, that last sentence on there. Atomic number is defined as the number of protons in the atom. The mass number is the number of protons plus the number of neutrons. An isotope would be two atoms with the same number of protons, but a different number of neutrons. That's described down here. Also, these side boxes do a great job of highlighting some definitions from time to time. And if we have an ion, that's bottom page 64, an ion has gained or lost electrons, and so a cation would be a positive ion, an anion would be a negative ion. So to get a positive ion, you have to lose electrons. To get a negative ion, you have to gain electrons. The example problems are taken mainly from the book, not entirely, but mainly. If you ever see a symbol 226RA, that 226 in the upper left-hand corner stands for the mass number. You could also see that listed as RA-226. So you have to find a periodic table, and RA is element number 88. That means that there are 88 protons, and the rest of the mass must come from neutrons. So 226 minus 88 leaves me with 138 neutrons. If there is no mention of a charge, assume that the particle is neutral and that the protons and electrons equal each other, so there also be 88 electrons. Now the second example on there is another isotope of radium. It's 217 radium. Sometimes they put the atomic number in the bottom left, sometimes they don't. Here the protons and electrons would be 88, but now the neutrons are 217 minus 88. Grab a calculator. 217 minus 88. That would be 129 neutrons. So this is a slightly lighter isotope than the one we had previously. The next example in the book does mention this 40Ca plus 2. The atomic number for calcium on the periodic table is 20. That means we know we have 20 protons. The neutrons would be the mass number 40 minus the atomic number 20. 40 minus 20 is 20. And it's not unusual for our smaller elements to have an equal number of protons and neutrons in their most stable isotope. When we have a plus 2 charge, plus 2, that means that we've lost 2 electrons. Normally we'd have 20 and be neutral. Now we have 18 with a plus 2 charge. That last example down there, going backwards, is here top of page 66. If I have 19 protons, that tells me which element it is. Element number 19 is potassium, which has the symbol K. So that will be the symbol I use to represent my element. I will put the 19 in the bottom left-hand corner. In nuclear notation, that's where we write the atomic number. It says we have 20 neutrons. And so the mass number is the total of the protons and neutrons. 19 plus 20 is 39. So this isotope has a mass of 39. We might call it potassium 39 or 39 over 19K. And they gave us some info on electrons. Electrons and protons do not match. There must be a charge here. We have one extra proton as compared to electrons, so the charge is plus or plus 1. I tend to write it as plus 1 just to make that plus symbol stand out more. Okay. So those are the basic notes. We have homework problems centering around nuclear notation. Really not a whole lot of homework problems about the experimenters and how they discovered these particles, more about writing the symbols. You'll find Homework 1A listed at the bottom of your notes page that we've done so far. That's page 64. Problems 1 and 2, page 66, problems 3 through 6, which you see right here. And page 93, end of the chapter, 6 through 8, and question 10. Work on those. They're not going to be due at the beginning of the class tomorrow. Instead, we're going to give you some more notes on Thursday. Expect you to do a second part of this homework assignment, and then typically the next class period we would check the homework. With a double lesson on Thursday, the next class period is the second half of that Thursday class. So you want to do the homework first. There'll be an online turn-in for that homework on the second folder. You do want to check the answers in the key, which is part of the online textbook in Schoology, before you enter those answers in, because we'd like you to have checked to see if you're right or not, and then to figure out how to be right before you turn that homework in. Once you complete the homework, we'll have two other things for you. We will have a list of questions from old AP and IB exams that are typical of this kind of material, and we'll have a quiz for you, all in the second half of Thursday's assignment. All right, good luck on the homework, and we'll see you Thursday.